Okay, so they had discovered the um, the X-rays, photographic plates. Photography was also discovered, and they were basically looking at the um, like, you know, different elements, different compounds they were finding in nature, and they were studying the chemical behaviors and the properties of those elements, you know, as matter basically. So metallurgy was all the time, you know, constantly happening. So they were looking at rocks with all these different properties. And so Roentgen was working in his lab, and he was working, you know, on the photographic plates and X-rays and those things. So, you know, those, I don't know if you guys remember or know this, that in the olden days, they used to use these black colored photographic plates, which were like plastic, you know, like sheets. And those sheets had like all black color. And then these sheets were the that in a black and white photography used to come in play. Okay. So here's the thing now, focus on this top part, that Roentgen, I'm going to just make myself invisible here and not important. This piece also goes down here, and this also goes down here. Okay, so now just focus on this piece right here. So we had one man, he brought a rock to Roentgen, and he said that this rock is very hot. And it is, you know, he said, I tried keeping this rock in a refrigerator, maybe it'll cool down, or I tried putting water in it and making it that it was going to cool down, but it did not, nothing happened to it because it's still hot. So he said, I wonder, it's like dark, and he said it's very heavy also. So I wonder what it's made up of. So can you just look? So at that time, they thought that the rock was emitting X radiations, X-rays, right? Because they had discovered X-rays. So they said, okay, fine, we will. And on the other hand, Marie Curie was also working on radioactivity and so forth. So Roentgen says, okay, give me this rock. This is a weekend approaching now. I'm going to take the rock. He put this rocks in, he wraps it in a photographic plate, and he puts that photographic, because it's an important thing, right? So he puts that piece in his drawer, and he leaves the lab and he comes home. Next, you know, after 2 days, when he went back to his lab, he opened the drawer and he saw that his photographic plate, you know, had become like it had patches on it. And what are these patches? Where are they coming from? They're coming from that rock. So that means the rock is emitting some kind of radiation, which is affecting the photographic plate. So he thought that, well, it must be X-rays. So let's figure out what kind of radiation is that. So now, right now here, you see where the cursor is? He puts that piece, that rock, in a container, and this container is made up of lead, because lead, you know, can stop the X-rays, and it has only one little opening here. So anything that is rays that is being emitted is going to come out of this little hole, and he wanted to study what are these made up of. So the first thing what he did was he put 3 photographic plates in all these different angles, and then he said, okay, let's see what's happening. So the radiation, one of the radiations, he found that these all these photographic plates had patches on them. So how did that happen? Or what he started to study the patches, like what could these patches, what could he understand by these patches? So some of the rays, he figured out that there might be some rays that were going straight. When they hit this particular photographic plate, they were very much condensed in a small space. So in other words, these photographic plates um, were like kind of like what do you call, like detectors, kind of. And so the radiation that struck this photographic plate, it was like very focused. So it must have been something very sharp that was going straight. Okay, that's one thing. But another thing was this one, the one that was on the top, these were lighter. That means some very light radiation has touched the photographic plates on the top. That means that some rays that fell on the top were not very intense. But he also studied, like, look at this parabola, this type of like the curve in the arrow. So these were spread all over. So it seemed like this was like something very heavy was here at the bottom. So that is why this was all were like spread out, like as if like the milk was spilt on something, like that kind of a feel it got. So this is one thing. Next, he said, okay, let me charge these, let me put these, see if these radiations are charged. So he put like these electrodes. Okay, so the top one is a cathode, which is positively charged. The bottom one is anode, negatively charged, and then you have this middle electrode. There's no charge on that. So he wanted to see, another thing is, will these radiations be attracted? So he found that some of the radiations went straight and were not attracted to the positive or the negative electrodes. There were some that got attracted to the cathode. That means positively charged electron. That means they have to be negatively charged radiations that is touching the top part, which is the positive electrode. And there were radiations that were heavier and spread out more. These were the ones that must be positively charged because they're attracted to a negatively charged electron. Next, he wanted to see if he could block these radiations with something. So he put these in a box in that same lead chamber and one hole, and he put a paper, a very thin shield of lead and a very thick shield of lead, just to see, what would happen. Can you stop them? And yes, these radiations that were heavy, and again, these are again photographic plates. So the ones that were heavy, they could be stopped by the paper, and he could detect them. The moment they struck the paper, they bounced off at an angle, and then he was able to detect them at this electrode, at this photographic plate. So these are alpha radiations. But gamma radiations and beta radiations, these two radiation passed through the paper. Next, the beta radiations, they got stopped by the lead, a thin shield of lead. So he could detect them at this, photographic plate or a detector. But there were some radiations that passed through the paper, passed through whatever thickness of lead he had posed, and extremely thick pieces of lead could not prevent this one radiation, last one, and this one again, there's a detector here, and they could be detected here. So he said that, okay, this type of is not just X-rays, it is much more than that. So he said, okay, these are radioactive, and Marie Curie was also working on it. So they came up with these 3-4 radiations that were coming out from these type of elements, which were basically isotopes. Isotopes are like the elements that have the same number of protons and the same number of electrons, but different number of neutrons. So that is why they are heavy heavy in nucleus. Nucleus is heavy. Okay, so what were the names of the radiations? Alpha, beta, gamma, and then there is positron also. So what is alpha? Alpha is made up of like the helium particles, which is the mass is 4. That is why they are heavy. You constantly saw them, falling with the gravity. So the mass is 4. The charge is, the like the +2 is the charge, and then the beta radiations are like electrons, so they are very light. That is why they were jumping up. They defied the gravity, and they were, because they had no mass, but they were charged. They were negatively charged. That's why they got attracted to the positively charged cathode. So beta radiations are like the electrons. Positrons are also like electrons, but the charge is positive. And then there were gamma radiations, which are very strong electromagnetic radiations, which can pass through all these different thicknesses of lead shields and paper and all that stuff. So very thick. Okay. So first of all, let's talk about isotopes, because this piece that the guy brought to Roentgen, this was uranium. But later on, they found the similar kind of radioactivity. These are radioactive radiations, were also found in other isotopes also. But all those isotopes which were heavier isotopes, which were, unstable, you can say, isotopes, they were the ones that were exhibiting radioactivity. Now look at these isotopes of magnesium right here. Magnesium 24, magnesium 25, magnesium 26. Okay, so these are the 3 isotopes of magnesium. Out of it, magnesium 24 is more abundant. That 78% of the magnesium 24 is found on this earth. So it's present everywhere. Then comes magnesium 25. Magnesium 25 is 10%, 11% is found. Magnesium 26 is only 10%. So these are like very rare, these are also called rare earth elements, because in the sense that not like real rare earth elements, but they are found like in less abundance in nature. And The reason is because they are unstable. They're constantly decaying. And why are they decaying? Because they are emitting these radiations. After emission of these radiations, they are either become stable or they form something else. So which we're going to look in the next thing. But let's look at first. When you look at the periodic table, you are going to see the average mass of these isotopes. And how is that calculated? So if you look at this, first of all, the number of protons. Protons are 12. That is equal to the mass number, right? Number of electrons is also the same, 12. So the number of protons is what defines the atom. But look at the number of neutrons now. Neutrons is mass number minus the atomic number. 24 minus 12. So the number of neutrons in the first one is 12. The next one is 25 minus 12, that is 13. Then comes 26 minus 12, that's 14. So you see that the magnesium 25 contains one more neutron. Magnesium 26 contains two more neutrons. So that is why it is very little abundance in nature. So that's why it's very unstable. So unstable means they are constantly decaying. You know, they are decaying. Either they are becoming into magnesium, so getting rid of that neutron, you can say that. However, when we write the mass number of these isotopes in the periodic table, we take the abundance factor times the mass number. Abundance factor times the mass number. Abundance factor times the mass number. You add these up, it becomes 24.30. You see that? 24.30 is the average weight of all the isotopes of magnesium. So this is how we write. But now let's focus on more about the radioactivity. In other words, what happens when an atom decays and decays or gives away the radiation. So look at this. This is tungsten. Tungsten 159 is the mass number, and 74 is the atomic number. So tungsten is giving away alpha radiations, okay, alpha particles or the helium. These are like helium particles. So after getting rid of the alpha, so in other words, 159 minus 4 is 155. That's what it means. 74 minus 2 is 72. So that minus why? Because this has been released from the nucleus of tungsten. So that is why you have now, it has formed a new substance which is called hafnium. And in other words, the way you're going to balance this, you also look at this: 155 plus 4, 159, 70 plus 2, 74. Okay, so that's the way of balancing it. Next is look at strontium. Strontium is giving away beta radiations, which means the electrons like no mass, but -1 charge. So 39 minus 1 is 38. 90 plus 0 is 90. So that's how it's balanced also. And we know that a new substance that is formed is called ytterbium. So it's not strontium anymore. It's not a strontium atom anymore. Look at nitrogen. Now, this is one of the isotopes of nitrogen. Okay, nitrogen 17 and 7. So when it gives away one electron, so the mass is 7 plus 0, 7, and 18 minus 1 is 17. So this is the new isotope of nitrogen. So when nitrogen gives away, nitrogen 17 gives away one electron, it forms nitrogen 18. Okay, so it's 18 is like higher because it's subtracting this -1, so balancing. Okay, next is the look at polonium. Polonium is making palladium when it emits alpha radiation. Manganese becomes manganese 49 becomes manganese 50 when it gives away this one beta radiation. Carbon, which is black, solid charcoal, and solid, we can see it when it gives away one electron. In other words, one beta radiation, it becomes nitrogen, which is a gas, and it vanishes in thin air. We cannot see it. Okay, so this is the thing with all these alpha decay reactions. Sorry, not alpha decay, it's called radioactive decay reactions. So they can decay and give away alpha, beta, or gamma, or positron. Now look at the gamma. Now here we have technetium, metastable technetium. Metastable technetium M means it is decaying. It is already giving away gamma radiation. And gamma radiation, no charge, no mass. So that is why when technetium decays, it still remains a technetium. But this is a more stable form of technetium, means it is not radioactive. It is not giving away radiations. Okay, so here's the thing with the radiation also. Fine, we understand radioactivity is like when you give away all these alpha, beta, gamma radiations, and then you form a new atom is formed. So that is all fine, but it is time bound. Time bound in the sense that sometimes it can decay in a few minutes, in a few seconds, in a few hours, in a few days. It could take months, it could take years, and sometimes the years could be thousands of years. So this carbon converting to nitrogen, there is some time attached to it, and that time is called a half-life. Now, what is half-life? Half-life is, let us say, you start with 100 grams of a radioactive substance, a radioactive atom. After one half-life is passed, after one half-life, 50 grams of it is left. So after the second half-life, 25 grams of it is left. After the third half-life, 12.5 grams is left. After the fourth half-life, 6.25 and so forth. So half-life is really how much of the sample is left, like half of the sample is left after how much of that time period. So that how much time period is called half-life. So, you know, this decay on the board, of course, we show it like as if it is only one atom reacting and producing one. But think about it. It's thousands and thousands. 1 mole is 6.02 to 10 to the power 23 particles, right? So it's a lot of particles. So on the board, obviously, we just show like it's one atom is decaying, but in reality, like thousands and thousands of atoms are decaying. So half-life is in how much time period half of those atoms have decayed and half of them will be left. So then another half-life, so that's what the half-life means. Okay, so half-life concept is very important. Okay, next is so this is one type of reactions in nuclear chemistry which relate to the decay process, forming the alpha beta, the radiations, you know, these alpha beta gamma radiations. This is one piece. The second piece is um, the 1 minute. It's opening up. Okay, the second piece is not, so we covered this already. 1 minute, let me get the other one. Sorry about that. This one, no, this one. No, I need to open up the other one. Hold on. Okay, maybe that one. All right, yeah. So there are two other types of reactions. These are the fission reaction and the fusion reaction. Fission reaction is with the heavier atoms. Fusion reactions are with smaller atoms, really, really small atoms. Now, fission reactions, generally very heavy nucleus, which is like enriched, like this is an enriched uranium. Okay, this enriched uranium really means one of the isotopes that is heavy, right? So it's a heavier nucleus of uranium, which gets bombarded by neutrons. Now, how much of the uranium and what is the speed of the neutrons and how many neutrons are getting bombarded, all that is again a classified information. So we do not know anything, but we just know this very generalized reaction in which uranium gets bombarded by neutrons at a certain speed and that gives you krypton, barium, and 3 more neutrons and a massive amount of energy. So these 3 more neutrons go back and hit the uranium-235. And then again, it gives away 3 neutrons, and those 3 neutrons go back and hit the uranium, nucleus. So this cycle, this chain continues. And every step, a massive amount of energy is produced. And the byproducts are obviously, radioactive krypton and a radioactive barium. Okay, so now there is a slight change in the mass of between barium, krypton, neutrons, and uranium-235, and that is what happens to. So in other words, this reaction, fission reaction, is basically the interconversion of mass and energy. So mass can be converted to energy. Okay, so it's a very important reaction. Okay, so this is one piece. Next piece is when you are trying to fuse very small nuclei, and hydrogen is the baby of the periodic table. So these are the isotopes of hydrogen. This one, the one that contains one proton, one electron, and one neutron, that is called deuterium. And the one that contains one electron, one proton, and two neutrons, that is called tritium. Tritium tri, deuterium du. You see that? So tritium 3, hydrogen 3, and deuterium 2 fuse together. Again, this fusion happens at an extremely high temperature, like thousands of degrees Kelvin, thousands of kelvins. So when they are fused, they produce helium, and they produce neutron, and they produce massive amount of energy. That massive amount of energy is the energy that is, that sustains the life on this earth. So without that, without sun, we would all be dead, right? This planet is going to be dead, basically. Or life force on the earth is because of the sun. So we see that the fusion is happening in the sun, and we are getting the energy from there. So this is another type of reaction. So now what we are going to do in this lecture is, number one, I'm going to show you first, we're going to start with fission, because that's how initially this was discovered anyways. So fission, and when they bombarded the fission with neutrons and all that stuff, first we are going to see the energy, the misuse of this reaction, the very bad use of this reaction. And then later on, we are going to look at the positive use of this reaction. Okay, after that, I'm going to show you the various uses of the other reactions, the alpha, beta, and gamma reactions, these ones. Okay, I'm going to show you where all these reactions are applied in medical field, in environmental science, in agriculture, right? For different types of like dating processes, all those different things. Okay, so but mostly medical field. Then after that is done, I'm going to show you where we are heading next. This is where we are going next. Our next, alternate energies like we're exploring. So fusion energy is another piece that, that can help us give a new form of energy, a more clean energy. But there are some challenges to it. So I'm going to walk you through a nuclear reactor. So, but first, let us look at, so the way I teach this lecture, this thing is all lecture based, on video based lecture. So you're going to watch the video, and after that, some little discussion. Okay, so let's see, there's some chats here. Oh, now it's fine. Okay, how long will the class be for? Okay, so I'm going to look at all these answers later. Let's focus on let's finish this piece off, and after that I'm going to answer the questions in the chat. But whatever questions come to you, you can answer through the chat, and let's communicate also. So let's look at this one.
Get your home and everything in it covered in just 90 seconds. Old insurance kind of sucks, but limited.
Oh.
And we were on that Palm Run for three and a half minutes. Tom and I are talking.
Christ, Dutch, you never sat on a bomb run this long over Germany. They'd have blasted us out the sky.
Yeah. He said, nothing there. No opposition, no nothing. Or anything. Just, just going to bomb the target.
I saw an aircraft, like a tiny silver drop, entering the sky above Hiroshima. I instantly recognized it as an American plane, as no Japanese aircraft could fly at that altitude at the time.
It was just one plane, so I assumed that it was passing by as usual. You knew I should have. I was content. Ichini-san.
I was wiping the desktop. That was when the bomb was dropped.
It took about 45 seconds from the time the bomb left the airplane until it exploded. And I think there wasn't a man in the airplane that wasn't either timing it with his watch or counting or doing something. I was sure the bomb was a dud. I was sure it wasn't going to work.
After falling for 43 seconds, the time and barometric triggers started the firing mechanism. A uranium bullet fired down a barrel into a uranium target. Together, they started a nuclear chain reaction. Solid matter began to come apart, releasing untold quantities of energy.
Okay. All right, guys. So here, okay, so, okay, guys. So what did you see here? What did you, like, what did you see? What did you understand? Let's discuss some things here. This was a really very bad use of nuclear, fission reactions, this whole technology. But what did you see? Yeah. Hello, are you guys even seeing? So, okay, so it was a massive, massive destruction of, life and people, like, property, and chain reaction had started. So let's look at this. The chamber reaction of the bomb, yeah, a negative use of nuclear power, a negative use of the amount of time it took for the reaction to start, right? The nuclear bomb being dropped and exploding over Hiroshima, yes. And the energy moving outwards, yes, exactly. Chain reaction. You saw the chain reaction, very good. So that's how it just drop it and then it just spreads out. Yeah. And Yeah, it's very sad. No. So we learned our lessons, this was like really a very bad use of devastation, complete devastation here. So, but that's not what science is about. Science is not about using this for these kind of destructive purposes. We are supposed to look at the use of this type of knowledge for more constructive, productive, peaceful purposes. So nowadays what we are doing is, because here's the thing, you're going to, let's explain this, what happened here. Nuclear fission, physical science. Yeah, here's the thing. So here is this reaction. Explain.
Art to me is really putting yourself in your work. I created this
Okay.
website called folkstudios.com. It was a play on words for old fogies because I didn't want to be embarrassed about being old. I wanted to say my age, not 39 and old.
Now, there's two important points to note about this. Here's a simplified picture of the reaction. The neutron plus the uranium gives us the barium plus the krypton plus 3 neutrons. The total mass over here is a little bit less. The total mass of the products of this reaction is less than the total mass that we started with. And what's happened is some of the mass has been converted to energy, and a large amount of energy has been released. And to give you a comparison of just how much energy, I'm going to compare this to TNT, which is dynamite. If you have one TNT molecule, and the reaction here is combustion, the burning or the explosion of a TNT molecule. Okay, let's imagine the energy released from the combustion of one TNT molecule, and we're going to call it X. Okay, one uranium atom splitting, and this isn't combustion, this is fission. The fission of one uranium atom releases an energy that would be 7 million X. So if you imagine the amount of energy released from one TNT molecule compared to one uranium atom splitting, you get a massive amount of energy released from a nuclear reaction compared to an ordinary chemical reaction. Why is there so much energy? Well, it goes back to Einstein's famous equation, E equals mc squared. The energy is equal to the mass times the speed of light squared. C is the speed of light, and C is huge. So C squared is extremely huge. C is 300 million meters per second. So you take that number and you square it, and then you multiply that by the mass, and that tells you how much energy is produced. So when a little bit of this mass disappears in the process of this nuclear reaction, a very tiny amount of mass can be converted into a large amount of energy, according to this equation. And that's why nuclear bombs are so devastating, or nuclear reactors can produce so much power from such a small amount of fuel. So that's the first point to note. When this reaction occurs, the total mass of the products is a little bit less than what went in, and that mass has been converted to energy, and you get a lot of energy from that reaction. The second point is that a chain reaction can occur, and here's why. Imagine our simplified diagram again. The neutron plus the uranium results in barium plus the krypton plus 3 neutrons. And these neutrons are flying out as a result of this reaction. Now remember, it was the neutron hitting the uranium over here that caused the fission in the first place. And as a result of this, 3 more neutrons are now flying around. And if this is happening inside a lump of uranium, these 3 neutrons over here can hit other uranium atoms and cause them to split. And when they split, more neutrons are produced that hit other uranium atoms and cause those to split. And you can see that the amount of uranium that is splitting is going to rapidly grow over time. And all of this can take place in a very, very small fraction of a second. Now, it won't occur in a small sample of material, because the neutrons escape through the surface and don't, once they leave the surface of the material, they don't collide with any of the other uranium nuclei. But if you have a large enough lump of material, what they call critical mass, then the neutrons collide with other uranium nuclei before they escape the surface. And this chain reaction takes off and the whole thing can blow up. And if it's done just right, this reaction can happen very, very fast and blow up with a massive explosion. And that's a nuclear bomb. Now, it's not easy to make this, but a simplified picture might look something like this. You take a piece of uranium like this and another piece, maybe it's shaped something like this, although exactly how this is done is all classified information. And you put an explosion back here behind it, and that fires this piece of uranium into the other piece of uranium, and both of these pieces would be what we call subcritical masses. When they get together, they merge into a critical mass, and at the same time, you're bombarding it with neutrons, and you get this massive chain reaction. But exactly how this is done, the velocities and the geometry, all involves some very complex calculations that only certain people would know, the physicists that work for the military who produce this stuff. And it's also very, very difficult to get enough properly enriched uranium to do this. So the theory here is relatively simple, but actually pulling it off from an engineering standpoint is very, very difficult. But that's a basic introduction to fission and how it was discovered and what's going on when the atom is split.
All you need to launch a culinary empire. Tools you claim everyone has in their kitchen.
They don't.
And a Squarespace website where you can brag about how you never went to culinary school.
All right. Okay, guys. So this was the one thing about.
Okay, welcome to the calculus class. You are about to embark on a mind-expanding journey.
Okay, so we saw, like, you know, that's the thing. First of all, it's really the relationship between the mass and the energy, right? E is equal to mc squared. So the mass gets converted. So, you know, obviously uranium gets bombarded, like we said, it gives you barium and krypton, and the difference in the mass is the rest of it goes into that massive amount of energy, which you saw just now. And I mean, this energy has to be trapped. So how do we use this massive amount of energy? So what we are doing now is using it in the nuclear fission reaction. The only problem with the nuclear fission is that barium and the krypton that it is giving you, right? It's giving you that barium and krypton, and the problem is that those are also radioactive. So we don't know yet what to do with these. I mean, to the best of my knowledge, I haven't found any information of what they're doing with the radioactive barium and krypton, except that calling it as a nuclear waste. And they had been dumping it, you know, initially in the oceans and dumping it in the deserts or, you know, uninhabited areas. So that has become a problem for us. That's one thing. Second thing is the nuclear reactors. Even though, you know, you are trying to use this energy for a purpose, for a more peaceful purposes, we're trying to see, you know, what you can do with that. But the problem is that sometimes it's just a whole infrastructure. If there is some mistake, there can be explosion to, like, just it's really cause more devastation. And one of the example is Chernobyl I think in Russia. So a few years back, you know, that whole nuclear power plant, it exploded. And like, the problem now with that is that all that radioactivity, it can be transferred through air to, you know, far away, all over the earth, basically, you know. So we are not very far from that place, you know. So we in California were getting the radiations from that, you know, the beaches in California. So this is the problem. But let us see, you know, what we are doing now. We are using this nuclear energy, nuclear fission energy in where is it? Nuclear reactor generating electricity. Is that the one? I think it's this one. Okay, so we are generating electricity now. And
In a pressurized water reactor, water is enclosed in 3 separate but interacting loops. In loop 1, water becomes intensely hot as it absorbs heat from the energy of nuclear fission. But because it is under very high pressure, the water doesn't boil and remains a liquid. Pipes from loop 1 wind through a steam generator tank that is part of a second, lower pressure water loop. Heat from loop 1 boils the water in the steam generator, and the energy from the steam powers turbines that drive electricity generators. The steam is then cooled and condensed in a heat exchange with a third water loop, which carries water from the cooling tower. The liquid water in loop 2 then returns to the steam generator where it is reheated and the cycle continues.
Okay, so you see that now we are just using it to, to basically generate electricity for us. And pretty much that is the only, main use we have at this point, unless something else is happening. I don't know that, but that's the main purpose for now. Okay, that's for the nuclear fission. So just hold on to the nuclear fusion. I'm going to take you into the nuclear fusion, nuclear reactors later on, but let's look at now the other radioactive, like the other uses of radioactivity. So one of them is obviously carbon dating, where you are using the, how you, so this is a, let's see. Yeah, so this is a, yeah. For, mummy or for other things.
Hi, I'm Chris Pryor, and I'm the manager of the Rafter Radiocarbon Laboratory here at
I'm going to speed this one up because it's a long video.
We date samples from all over the world and using radiocarbon dating. Radiocarbon dating is really basically pretty simple. All living things contain carbon, and there are 3 naturally occurring isotopes of carbon, 12, 13, and 14. As long as the organism is alive, it maintains a constant amount of carbon in its body. But as soon as it dies, it no longer takes in any new carbon, and the radioactive isotope of carbon, carbon-14, begins to decay away. So what we do in the sample preparation laboratory here is to measure how much less carbon-14 there is in the samples than there would be in a living organism. The first step in radiocarbon dating is a physical pretreatment. By that, what we mean is looking at a sample to see whether or not the sample is what it's supposed to be and whether there's any contamination in it. Kelly here is looking at under the microscope at a sample of wrapping from a mummy. A client wants to know how old the mummy is, and so has sent us 2 samples. One is wrappings from around the bandages around the legs of the mummy, and the second sample is from the interior lining of the coffin. In radiocarbon dating, it's very important to remove any contaminating carbon. So the second step in the procedure is to give the sample a series of chemical washes to remove any material that might have been added to the original carbon after it's been in a burial environment for some time. Then we go to the third step in the procedure. After the chemical washes, the sample is dried, and the third step in the procedure is combustion. In combustion, we place the dried sample in a quartz tube with copper oxide and silver wire, and then we evacuate it so there's a vacuum inside, and then it's flame sealed off to create a tube with a vacuum on the inside. Then that tube is placed into a muffle furnace, and in the muffle furnace, the sample is heated to 900 degrees overnight, and the solid sample then burns in the oxygen, producing carbon dioxide, water, and then sometimes some other non-condensable gases. The next step in the dating procedure is to take the carbon dioxide that we've collected out of the combustion tubes and make it into graphite. We go to this vacuum line, and the carbon dioxide is taken out of the mass spec bottle and put into a graphite reactor vessel where it's mixed with iron powder and hydrogen. CO2 plus H2O, heated at 700 degrees, will form graphite and water. The reaction vessel is put into the oven at 700 degrees for about 5 hours. And after that point, when we weigh it back, we get a small amount of graphite, just about the size of, a few flakes of pepper, and that's sent down to the accelerator for dating.
Hello, I'm Roger Sparks. You've seen how the laboratory turns the sample we want to date into a piece of graphite. Now we're going to see what happens to that graphite. We bring it over to this laboratory and we pack it into this little aluminium pin, which is called a target holder. The target holder can then be placed into a wheel like this. We can have 40 samples holders in that wheel, which means we can actually date 40 different samples at the same time. The wheel will get placed inside this device here, which is called an ion source. The purpose of the ion source is to pull the carbon atoms out of the graphite and fire them down the tube towards the accelerator like bullets out of a gun. In order to get them pushing fast enough to get to the accelerator, we actually put a very high voltage onto this ion source, 50,000 volts. That's why the source is enclosed by a cage. There are doors which we lock when we're running so that nobody can get in here and injure themselves. We also need a very high vacuum in the tube from the ion source to the accelerator. There must be no air that can impede the passage of the atoms. So to do that, we have vacuum pumps around the system, and there is one at the top, that cylindrical object, which is making quite a loud noise, but it has to run 24 hours a day to keep the vacuum there. Now, let's go and have a look at where the atoms go. Well, here we are at the main magnet after the accelerator. Now, carbon atoms are coming from the accelerator, which is in that large green tank down there, and they're traveling down the grey tube at something like 6% of the speed of light. When they come into the magnet, their path gets bent. So instead of standing in a straight line, they get bent through 90 degrees and travel towards us here. This magnet acts very much like an old cream separator that used to be on dairy farms. You know, you put the milk and the cream together, you spin them very fast, and the heavy cream goes to the outside, the light milk goes to the inside, and that way we can take the cream out through one spout and the milk out through the other. Well, we're going to do exactly the same thing with our carbon atoms. The radiocarbon that we want to measure is atoms are heavier than the ordinary carbon atoms. So the lighter ordinary carbon goes on the inside of the track in this direction, while the heavier radiocarbon comes straight out, past this tube, down towards the other end where we have our detecting device. Well, if you are a radiocarbon atom, this is the end of the line. The atoms come down into this grey cylinder, which is a detecting device, and that will generate an electric pulse for every atom that comes in. The pulse goes to the computer in the control room, and we calculate on the pulses that come in, and then we know the age of the sample that we've been dating.
Okay, so this video is like, you know, you see like how elaborate, just first of all, a really teeny speck of what is it called, pepper, like the black pepper, really tiny. That's the amount you need for carbon dating. So the whole process, I just wanted to show you the entire infrastructure. It's like billions of dollars are spent in carbon dating, how they do it. And I mean, I'm still like, still don't get the science or the math behind it, but suddenly, you know, this whole thing has its own place. And this is to determine the age of mummy, and not just the mummy, just in general, you know, different samples from all over, from all kinds of samples. So really looking back, you know, this is just amazing how this whole thing they put together for just dating the samples. Okay. So anyways, so that was the carbon dating. Now we are going to look at the use of these elements that give away radiations, you know, alpha, beta, gamma. They are used as tracers. And now the thing is, this is a good video, but the problem is the audio is not very good. So I'm going to walk you through this.
Radioactive isotopes have various benefits for various things.
Now I'm going to just, yeah, the audio is not good, but I'm going to just,
testing of neutron.
Okay, look at it here. What they're doing here is that they take the tracer element, which they know is emitting some kind of radiation, whether it's alpha, beta, gamma, whatever radiation. For example, phosphorus, one of the isotopes of phosphorus. And let's say whatever radiation it is emitting, we know we can detect that. Now, they take the fertilizer, they lace the fertilizer with a radioactive tracer, and they drop it in the soil. Then they notice whether the plant is absorbing that fertilizer or not. Once the plant is absorbing that fertilizer, then they want to see, you know, how is the plant progress? Has the plant you know, has grown and it's healthy, or it has died, or it's whatever has happened. Okay, so this plant, if it has absorbed the fertilizer, has the fertilizer traveled to all parts of the plant and made it like nice and healthy, or what has happened? So this is how they test, you know, they make fertilizers and then they test the effectiveness of the fertilizer, or the, you know, the fertilizer through the detection, you know. So they take the plant and they put the detectors, and then what happens is that if the detectors, they actually detect the radiations coming from the plant, and of course from the soil also. So if they are able to see, you know, it has been beneficial to the plant, then, you know, they go and, you know, they do whatever they need to do with that plant. So for detecting purposes, we use the radioactive tracers. And then there's another example here, and this example is of you know, insecticides. So we make these insecticides, and we want to make sure, very important, that the insecticides only kills the pests, the pesticides or the insecticides. They only kill these little bugs which destroy the plants, right? And they want to make sure that the plant is not absorbing the insecticide. So this is like a very selective process. So in this case, what they do is they take the insecticide, and let's say the insecticide has a chlorine or fluorine or iodine or something. So this insecticide, they put a tracer inside the insecticide, or they make the particular insecticide radioactive, right? And so it has that particular radioactive chemical in it. And so then they spray it. Now they want to make sure that the bug has absorbed that material. So they are going to detect the radiation coming out from the bugs. If the bugs have absorbed the radiation, very good, good insecticide. But they also want to make sure that the plant has not absorbed that insecticide. So if the plant is also showing radiation, no matter how much of these bugs have taken the insecticide, it's not a good piece for us. So that leads to a new research. A new research is like, okay, we know that this is being absorbed by the insecticides, but we want to make it selective so the plants don't absorb it. So what else can be done? So that leads to new, research. So that's this whole piece of research and development. So that's an agriculture environment we are using. And then also we use these tracers in detecting, organs in the body that are malfunctioning. So apparently outside, you can't see like what is happening to an individual. So what they do is they put the tracers inside the human body, and then they see, now here's a very important piece here. Try to understand this. All those people are going in medical field. When a medication is given to an individual, and that medication could be anything, is given to an individual, that medication should be absorbed by the human body. It should be distributed by the human body. It should be metabolized by the human body. It should be excreted by the human body, and it should not cause any toxicity inside the human body. And the same thing goes for the plants and animals and whatever, especially animals. So veterinary sciences, same thing. So this is called the ADMET profile. ADMET is ADMET profile of the drugs. So here, in this case, they have the nuclear medicine, the radioactive tracer as a kind of a medicine, where we're trying to detect inside the body, where are the problem areas. So let us say this is a patient with some problems in the thyroid gland. So when you take the body, when you inject the tracer in the body, the tracer, it travels inside the body and it reaches those areas also where there could be some blockage, where the things are not, the distribution, excretion, all that ADMET profile is going to work. So they find that, then they detect those radiations. Where are those radiations coming in the human body? Is it the kidneys? It's the thyroid? Is it some other part? Where is that accumulation, you can say, of that particular tracer? That is a problem area. So in this case, it is the thyroid, okay? And then the last piece here is, anytime you see a fan with all these squiggly arrows, that means that is a radioactive zone. That is going to be that's a nuclear zone. So it is it's a dangerous area, so you should run away. So these two signs, this is what it means, just run away from that place. Okay, these radioactive radiations can be very deadly. So here's the thing, the alpha radiations, fine, you can prevent them by paper, so you're okay. Beta radiation, yeah, they penetrate the human body, they can penetrate your flesh, right? And they can cause scarring and, burn your flesh, burning sensation, those things. But gamma radiation, they can penetrate your organs, damage the organs, immediate death. So that's the thing with them. So anytime you see this sign anywhere on the road or anywhere, that's what it means, okay? Now we are going to use the, how do the PET scans work? So look at this.
Scan creates 3D images of the body. It does this by using radioactive tracers, which are usually administered to a patient through intravenous injection. The tracers are made up of carrier molecules that are tightly bonded to a radioactive atom called an isotope. The carrier molecule can interact with or bind to specific proteins or sugars in the body. The carrier molecule that will be used depends on what the doctor is looking for. If she suspects cancer or is monitoring a known cancer's growth, she may use FDG, a modified form of glucose, which gets absorbed by tissues. When tissues absorb a lot of glucose, it may indicate a cancerous tumor. The radiation from the tracers poses little danger to the patient since they quickly pass out of the body. The isotope produces small particles called positrons, which interact with surrounding electrons. This interaction results in the complete annihilation of both particles, releasing two photons that speed off in opposite directions. The detectors in the PET scanner measure these photons and use this information to create an image of the distribution of FDG in the body.
Okay, so here's the thing. How do we give these tracers? How do we inject the tracers in the human body? So obviously they put them in some kind of a carrier molecule. So in this case, it's basically sugar, a glucose, because it's going to distribute evenly in the body. So they take this glucose and that carrier molecule, they put the tracer element, because tracers are what? They are just, elements, metals basically in nature, which are radioactive. So you can't like put them in some kind of a molecule, like just, you cannot like they have to be injected in some way so their body can accept them. So you put them in a syringe which has a glucose, goes inside the body. Then that glucose travels in your body, of course, gets metabolized or whatever, and then it goes right in these areas where it sticks in those places which are the problem areas. And so through the detectors, you can detect them. So let's look at what are these detectors, how do they look like? Radioactive tracers, I think it's this one. How do the PET scans work? Okay, maybe that's the one. 1 minute. Yeah.
The nuclear medicine department of a hospital uses radioactive materials every day. They're used to help doctors understand what's happening inside people's bodies. First, a radioactive material called a tracer is prepared in a specially protected area. It's designed to accumulate in a certain part of the body. This syringe contains a tracer called technetium-99m. It emits gamma radiation and is one of the most commonly used radioactive materials in nuclear medicine. Once the tracer is ready, it's injected into the patient. In just a few minutes, it'll accumulate in the target organ, in this case, the kidneys. The doctors are trying to find out if this patient's kidneys are functioning properly. Gamma radiation is very penetrating. It easily passes out through her body. She's carefully positioned over a machine called a gamma camera. It detects the radiation and pinpoints where it's coming from. A series of images are collected at regular intervals. The first image captured by the camera clearly shows the size and shape of the two kidneys. Now watch what happens over the next 15 minutes. The radioactivity in the kidney on the right has almost disappeared. This kidney has quickly got rid of the tracer, but there's still a high level of radiation being emitted from the kidney on the left. There's probably a blockage. The left kidney is struggling to get rid of the tracer. But if the radioactive material is inside the patient's body, does this make them radioactive forever? To investigate, a syringe containing a fresh sample of technetium is placed into a radiation detector. At 9 o'clock in the morning, the radioactivity of the sample is 112 million counts per second. After 2 hours, it's dropped to 88 million. After 4 hours, it's 67 million. The level of radioactivity emitted from the technetium sample is gradually decreasing.
So you see, here's the thing, very important. Fine, we understand that these radiations, they are, these radiations, they can be detected, and fine, we understand that where they are going to accumulate most, we can detect them through the cameras and all that stuff, and we would know which of the organs is not functioning properly. All this is great. But what is important is that when a patient is injected with a radioactive tracer, that person becomes radioactive. So that the entire body is basically emitting radiations. You see that? And so these type of people, they cannot just go around walking in public here and there. Like a long time back, they used to allow them, and then the other people would be affected. So what is important is that, and that's where this whole research and development piece comes into play, where the individual who is injected with the radioactive tracer, first of all, needs to be staying in one place, quarantined pretty much. And second thing is that the radioactive tracer should go in the body, do its job, and quickly gets eliminated from the body. So it should be a substance, number one, which is in a very trace amount. That's why they're called tracers, small amount, number one. Number two, when it goes into the body, it should quickly, should have a short half-life. Short half-life means that it has done its work and then it's degraded and it has become something else. And the new thing that it has formed should not be toxic. You see that? So it's a whole new paradigm of research in this area. However, the nuclear medicine is itself a big thing where people are, trained, staff is trained very particularly to handle all these, different like the pieces of, using the radioactive tracers. One thing I would like to say, since about the career management, that yes, it is a good field to go in. And yes, if you can, get some kind of a certification or training and you can work in this field in nuclear medicine, I think the pay should be good because, the hazard is there. But at the same time, do not stick into this field for a long term. So a few years you can work there, but afterwards, you should think about, transitioning into a field which is more like, which supports nuclear medicine. There are so many other businesses, like softwares, like people, like you can work in a software industry, IT, you can work in like the people who make machines, the people, just so many sales, marketing, business side of things, you can look into that. So it's good to work in these laboratories, but at the same time, not for too long, because in the end, it's the people who are working in this field are the ones who are getting exposed to the radioactivity almost every day. You see that? So even though you have all these, preventions, and even though you have all, like procedures, safety procedures, but I think when the exposure is long term, every day, then it can be, a health issue. So, think very wisely. I think there are colleges here. I think one of the college, if I'm not mistaken, is the college in it's a community college which gives you those bachelor's degrees in, I believe, nuclear medicine or radiology or something, so like I said, those are good areas to work in, but long term, they can be, health issues to it. So keep that in mind, okay? Anyways, but there are so many other careers, I have a video here on careers, so you can look into those careers also. So, it's not a bad thing. Okay, anyways, now here's the thing. Now they're making a change because positron emission tomography involves like using a tracer. It's giving you inside, it's injecting positrons. And then we have electrons in the body, electrons and the positrons annihilate each other, produce gamma radiation. Gamma radiations are detected on the detectors and the computer scans it and creates all those images. So PET scan is one thing. But MRI only does not do any injections inside. MRI is all about, using these radio waves to calculate, what is going on. So it's like, let us look at like the PET scan versus the MRIs. Okay.
In positron emission tomography, radioactive tracers emit positively charged electrons called positrons. These positrons encounter electrons and they annihilate each other to produce two gamma particles. Gamma particle detection from several angles in conjunction with computer imaging produces accurate images of soft body tissues. PET is particularly useful in diagnosing Alzheimer's disease in brain tissue. Nuclear magnetic resonance imaging, or MRI, is a popular diagnostic technique because it does not submit the body to dangerous high-energy particles. MRI is performed by placing the person in a large cylinder that contains a strong magnet. The magnetic fields of the atoms of the body are caused to resonate by the introduction of radio waves. A computer interprets the signals put out by the resonating atoms to produce a two-dimensional view of the body. The MRI is especially useful in detecting abnormalities in soft body tissues.
Okay, so you see that the PET scan, you're injecting things, but MRI is more like, I think it's less invasive, you can say that. So that's one thing. Now, regardless, whenever there's a radiation that is sent in the body, whether you're bringing it inside. So see, in PET scan, you are generating gamma radiation from inside your body. That's why it's a little bit dangerous. But whenever your body has exposure to radiation, the cells are killed. Okay, so let's look at this video, what happens to the cells.
Let's see what happens when radiation penetrates the body and attacks the cells. What is a cell? And what happens when it is attacked? It's a simple organism which reproduces itself by dividing. Our bodies are made up of millions of cells. They're the building blocks of our blood and tissues. Now, powerful radiation strikes, and cells are injured or destroyed. If radiation stops before the accumulated dose is too great, almost all of the damage eventually will be repaired. If radiation continues, there are some cells less able to function at top efficiency. Should the body fall behind in its recovery, severe illness or death could result.
You see that?
The key then is the amount, the total dose of radiation received.
So the total dose of radiation received, that is that's the main key. So, so your body should be able to withstand that amount of doses. Okay, so that's the thing with with these radiations, that go inside the body and for all the purposes. But now let's look at the nuclear fusion.
Fusion is the nuclear reaction that fuels the sun and the stars. When two light atomic nuclei, such as deuterium and tritium, each a version of hydrogen, unite to form a heavier nucleus, like helium, the bonding process will release energy. Deuterium is composed of a proton and a neutron, tritium of a proton and two neutrons. The nuclei are positively charged and naturally repel each other. To overcome that resistance, the nuclei must be energized with extremely high temperatures so that they can collide with force. As temperature increases, so does the kinetic energy of each nucleus. With greater temperatures, each nucleus will move randomly at progressively higher speeds. When the temperature gets high enough, the kinetic energy of the nuclei overcomes the repelling forces and the two collide. The collision of tritium and deuterium yields a helium nucleus composed of two neutrons and two protons and a free neutron. but it also releases a tremendous amount of energy in the form of heat. The sun is a sustained fusion reaction. The challenge for physicists now is to develop sustained, controlled fusion as a source of power.
Okay. All right, so that's where we are heading. Our future is heading, where we are trying to trap the power of the sun and trying to use that for the alternate energy, for the alternate energy sources. So the only challenge is the very extreme high temperatures, like several thousands of degrees, several thousands of Kelvin. And that's one thing, although all we need is hydrogen, deuterium and the tritium. These are the two, isotopes just fused together, and that's all. And then is how do you generate that energy, and how do you trap that energy, and how do you use it for helping the mankind? So that I'm going to walk you through nuclear fusion, a power plant. But let us just look at this thing. Where is that? Nuclear fusion animation. Just this is how it is. All these different fusion reactions. Okay, so these are like the different types of fusions. Basically, just fusion is the fusion. So let us look at now, looking at the nuclear fusion. This is a very important video. This is where, like I'm saying, the future is heading, and one bucket of water can really suffice your energy needs for 30 years. And how is that possible? Let's just look into this.
But some scientists have their research sights set on the Earth's ultimate energy source, the sun. But they don't plan to harness its power, they want to imitate it. The diameter of the sun is about 100 times that of the Earth. It's a giant ball of pure energy. The sun produces enough energy every second to power our planet for 1 million years. The sun's energy is generated by nuclear fusion. But we don't need to travel 180 million kilometers to harness fusion power. It can be generated here on Earth.
Fusion is important because it's something that's going to give us a really, really long-term sustainable energy source.
Scientists at the Joint European Torus Nuclear Fusion Research Facility near Oxford are investigating fusion for its potential to provide an unlimited supply of cheap, clean energy.
We are taking the power source of the sun, which is something very ambitious, and I think it's something very worthwhile attempting to do.
In 1945, the world discovered the power of splitting the atom. Today, all nuclear power plants split atoms in nuclear fission reactors. The main drawbacks are a lack of good options for the disposal of spent fuel and the danger of an accident that releases radioactive material into the air or groundwater. But a fusion power plant would produce no deadly radioactive waste. It can't melt down and uses a clean and abundant source of fuel. Inside the Torus experiment, atoms aren't split apart. They're fused together.
It's a process that uses no radioactive plutonium or uranium. The fuel is hydrogen. Hydrogen atoms are heated to 150 million degrees centigrade, 10 times hotter than the sun's core. At this extreme temperature, the atoms turn into a plasma. The plasma atoms collide and fuse. Energy is released when the positively charged plasma ions overcome their natural repulsive forces. It's 1 million times more efficient than today's nuclear power stations, and 1 trillion times more efficient than fossil fuel. This clean energy confines the high-temperature plasma with magnetic fields. The technology is inherently safe, but the experimental machine is expensive. So more than 160 safety checks take place before the countdown to ensure there will be no damage to the machine.
Everything we do, we need to be totally sure we've got everything right. We can't afford any mistakes, and it can be a little bit tense at times.
The machine is housed behind 2 meters of concrete and steel.
Trigger the pulse, please.
The camera monitors the experiment. The glowing light is plasma, superheated gas, which can reach 200 million degrees. The reaction produces energy like any star in the solar system. Nuclear fusion here on Earth.
We did good. Excellent. That worked exactly as we wanted it. It's perfect. I'm happy. I think the scientific coordinators are very happy. You can see lots of smiles. That's which is good.
Nowhere in the world have scientists come closer to creating the ultimate energy source. And the fuel for fusion is virtually unlimited.
1 bathful of water would provide enough energy through fusion to supply one person with all their energy needs. So their transport, their heating, their food, their industrial needs for 30 years.
Because fusion is fueled by hydrogen, there are few security risks. Research is still at the experimental stage. Scientists estimate it will be another 30 years before there will be a commercial fusion power plant.
This is a very long-term strategy. This isn't something that's suddenly going to produce a result tomorrow and solve all our problems. We will get there. I don't think we have any choice.
Visionary scientists and entrepreneurs who are developing renewable clean energy solutions will be able to offer us viable choices. The planet's increasing population and expanding energy demands may well depend on them.
You see that? Oh my God. This is just something. How they did all this. If you like really paid attention to this, this is like 150 million degrees Celsius of temperature. And in that power plant, which is basically made up of concrete and steel, they were able to generate the plasma. And again, that is how this is all, I don't know how they're going to do it on a large scale. That is a big problem. But if this works, then see, we don't have any waste. We don't have any nuclear waste like in nuclear fission. There is a lot of waste. Here we don't. And the hydrogen that we need to fuse, that is available in the oceans. So with that said, if you really think through, the next, era is going to be for the waters, where, the monopolies are going to be for the waters. And once, if this fusion if we are able to, you know, somehow get this whole logistics into how to provide it to the people, you know, how to make it available to the people, then yeah, oceans are going to be the big war is going to be for the oceans then. So we will see, you know, where the world is heading. But we are all the time looking for energy sources like solar energy, you know, wind energy, and so many others. So the efforts are going on. So anyway, so I'm going to now stop recording, and if there are any questions.